teach this in the past, it would be with a lot of hand waving. I'd be like, all right, so then you do this, then you do that, and I just walk you through it by example. And then OpenStax became a thing, and I was like, oh, they have a step-by-step approach that isn't idiotic. So let me just copy and paste that in there, but I just kind of blindly pasted. I was like, it looks good here, paste. So turns out it's a little too early, but it's all right. I can read through it though. First step, put the equation in standard form and identify P of X and Q of X. So right off the bat, I'm putting into action the thing that we talked about on the previous page. Then we calculate the integrating factor. This is the component that makes the whole thing work. All right, e to the integral of P of X dx. And then we multiply the equation by that. All right, the reason why we do that is to make the left-hand side of your differential equation the result of the product rule for derivatives. All right, so this here needs to be the result of the product rule for derivatives. You know, because you have a product rule for logs also, and some people actually call integration by parts the product rule for integration. No, it's specifically the one for derivatives. Okay, so if I were to take two functions that are being multiplied, and find their derivative, or find the resulting derivative of that product, it should end up being whatever the left-hand side is. All right. So what I'm going to do is first test to see if that's what I have. All right. The way I test is by taking the components that are not derivative based and make a product out of them. All right. So looking at the left-hand side here, I have an x minus 2 and I have a y. Basically anything that doesn't have a prime involved in it is a candidate to be part of my product. I need two things. All right, so I'm going to take a stab at it and see if it works. All right, so the derivative with respect to x of the product of x minus 2 and y. All right, so that should be the first function. It's really crazy how everything lines up, because in my Calc 1 class, yeah, the whistling, yeah, it's crazy. Yeah, it's the wind. It's like being trolled here. No, in my Calc class in high school, like today, we're talking about the product rule. So it's like there's always that. It's kind of crazy how it works out. It's like when we're using the unit circle in calculus, it's almost always the same day that we're learning about it in pre-calc. It just like it always works out that way. It's crazy. All right, so the first function. Here's my first function. Multiplied by the derivative of my second function. I don't know what my second function is, so I'll just note it as y prime or dy dx plus my second function multiplied by the derivative of the first function, which would just be a 1. All right. So if you suspect that you have a first degree or linear differential equation, you can always test this out. You can grab the parts from the extended form on the left-hand side that do not involve a derivative and find the derivative of that using the product rule. If it ends up being what you have on the left-hand side, then you're ready to rock and roll. You don't even have to do a substitution. All right? Because what we just discovered is that on the left-hand side of the equation, we already have everything that we need. Because this is what it simplifies down to. That's what the left-hand side of the equation is. What that allows me to do is replace the left-hand side of the equation with that derivative expression. So replaces the left-hand side of the equation. So b dx of x minus 2 times y would itself be equal to 3x squared plus 2x. All right, left-hand side gets replaced with that expression. So now what I can do is multiply both sides by a dx. My differential equation is in differential form now, and integrate both sides. Derivatives and antiderivatives are inverse operations, right? Which means that they cancel each other out. So when I take the antiderivative on the left-hand side, I'm just left with x minus 2 times y. On the right-hand side, x cubed plus x squared plus c. I want to get y alone, that's the whole point. And so what I have now is my solution where y is equal to x cubed plus x squared plus c over x minus 2. And that is the solution to the first degree linear or linear differential equation. All right. So again, the differential equation is in the same form that a line would be in, but it's not actually a line. Okay. Antiderivative. Well, I suppose it could be. Actually, in this case, if I differentiated it out, it'd be, part of it would be linear, but then another part of it would be rational. So, coincidentally. All right, so let's actually do one where we have to do a substitution. The second problem is that it's still already in the right form. It's y prime minus something times y equals 4x plus 3. All right, when it's in this kind of form, that's when we know, or at least we have a sense, that we're going to have to do something more. At least come up with that that multiplier. All right, so let us investigate. First thing we do is figure out what the p of x is going to be. That's going to be the coefficient of y. And q of x, which ends up not being needed in this type of solution, but it's useful for other things. I just need the p of x. So mu, Greek letter mu, of x is equal to e times the integral of p of x dx, which would be e times the integral of negative 2 dx. As integration goes, that's not as tough as it could be, because that's just e to the negative 2x. We don't put the plus c in. All right. We save the plus c for the very end, when we actually solve the differential equation. Well, there's plenty of opportunity later on to put a constant c in there. We don't need it here. All right. This is just acting as a multiplier. And besides, if I did do a plus c, that's just telling me that I'd be multiplying the equation by some arbitrary constant. That constant is not what makes this a problem. It's the x's and the y's that are making it the problem. So if I have a c that I'm multiplying the entire equation by, that does nothing. All right. What I'm going to do is take my original differential equation, y prime minus 2y equals 4x plus 3, and multiply the whole shebang by e to the negative 2x. So on the left-hand side, I'm going to get e to the negative 2x, y prime, minus 2e to the negative 2x, y, equals, and then on the right hand side, I'm just gonna, yeah, I might as well just distribute it. I was gonna say I'm gonna leave it undistributed, but it's not too big of a deal to go both ways. Either way. All right, so this just took something that looked relatively simple and made it ugly. But this ugliness needed to happen in order to play out. All right, so what we're looking at is on the left-hand side, after you do this multiplication, this should be the result of the product rule. So we should have the first function multiplied by the derivative of the second, plus the second function multiplied by the derivative of the first. So if I wrote this as the derivative of e to the negative 2x times y, again, just grabbing any part that's not a derivative. All right, the weird thing is we're looking at that negative 2e to the negative 2x and saying, well, that's not a derivative. I don't see a prime there, but it's implied. This actually is the derivative of that. If I took the derivative of e to the negative 2x, this is what I get. All right, so it's kind of a hidden derivative. All right, so you just, I mean, talking to yourself a little bit is helpful here. That's how I do it anyway. I look at this and say, this is supposed to be first times the derivative of the second. So this is my first function. This is the derivative of the second. So without going any further, I know that my second function has to be just a y, because the derivative of the second function is y prime. And then I just test it out and see. So then I would have the second function, y, times the derivative of the first. Derivative of that is negative 2e to the negative 2x. All right? So that's going to pretty much get us where we need to go. It's just we have to do a little bit more work than the last question because the right-hand side looks terrible. But anytime you have exponential e in an integral, it's never going to be that terrible because there's a lot, there's a pathway. If you just have an e, then it's going to be pretty easy to figure out the antiderivative. If you have a product, then it's in all likelihood going to be integration by parts. So bottom line is you're going to be okay. All right. So kind of save yourself a little bit of time and energy. Since all I'm going to do is rewrite this with an integration symbol, I'm going to move the dx to the other side. This is going to eventually just become an e to the negative 2x times y. I don't have to show all that intermediate stuff. We'll just clean that up a little bit. It looked terrible. And then just carry down these guys. So the big challenge is on the right-hand side, because I'm going to integrate both sides, but the integration is going to cancel with the derivative on the left. I actually have to do it on the right. All right. So a little bit of work ahead of us, because this is two separate integrals. The integral of 4x e to the negative 2x dx plus the integral of 3e to the negative 2x dx. All right. First one, you have to do that by integration by parts. The second one, it's a rule. It's knowing how to take the derivative and antiderivative of an exponential e. All right. Since I know that part of it is going to be e to the negative 2x, I can start from there and just say, okay, well, what would the derivative of that be? It would be e to the negative 2x times a negative 2. Well, I don't want a negative 2. I do want a 3. So it's the same thing I did before. I did it with a log before. I did it with an e here. You could do it with trig functions. Any transcendental function is going to play out that way. It's you get a sense of what the antiderivative ought to be. I know it's got to be some form, some coefficient of e to the negative 2x. E to the negative 2x is a derivative of negative 2e to the negative 2x. The negative 2 has to go, divide it out. The 3 has to come in, multiply it in. All right? And that's so that you don't have to waste time doing u substitution with that. All right? The other part is the parts, the integration by parts. And that, there's no way around it. Unless when you write your index card, for whatever reason, you put down like a solved example of an integration by parts question, and for whatever reason it ended up being exactly this question that you had on your note card. That's the only way I can see a person going from here to the final answer without showing any work. Right? And that's actually happened before, where a person was like, let me just copy down this particular example. You never know, it might come up. It came up. Almost exactly the same with slightly different numbers, so you never know. I'm not hinting at anything, except I probably am. So u would be 4x, dv would be e to the negative 2x dx. Remember, when you're deciding on your u and your dv, the dv, you always start with something that you can integrate. If you can't integrate it, then it's not your dv, all right? When you're choosing your u, it's something that you want to be able to differentiate, but it also needs to become a simpler function when you differentiate it, all right? This is going to become du equals 4 dx. That's perfect, all right? V is going to be equal to negative 1/2 e to the negative 2x. So uv minus the integral of v to u so we're looking at 4x times the negative, I'll just highlight it, 4x multiplied by the negative 1/2 e to the negative 2x. So we're talking negative 2x e to the negative 2x minus the integral of v du. All right, so that's where we're taking, I'll go green on my highlighter. So that's these two. Oh, that's too dark. That looks terrible. I'll just circle it, I think. So du. So multiply those two together, and we're looking at negative 2, so that'll make the negative negative into a positive. 2 e to the negative 2x dx. You can leave the 2 inside or outside, it's not going to make a difference. All right. So now that's something that's much easier to integrate. So negative 2x e to the negative 2x plus 2 times, well, we already figured that out, it's negative 1/2 e to the negative 2x plus c. That's all equal to the left-hand side, which is e to the negative 2x times y. All right. So now we're in the end game. I mean, we were in the end game a little while ago, but once we establish the appropriate u and dv, the problem is pretty much going to solve itself. And that's because you notice I need to get y alone, but each term has an e to the negative 2x in it, except for the c, but that's fine. I'm going to divide everything by e to the negative 2x. Or I can multiply everything by e to the positive 2x, however you want to think about it. Sorry? Oh, I need the negative 3/2. Yeah, missed it. Thank you, thank you. So minus 3 over 2 e to the negative 2x Then we have the plus c. All right, so then all of this stuff is going to get divided by e to the negative 2x. And so we'd be looking at y equal to negative 2x minus 1 minus 3 halves. We'll get that in a sec. Plus c over e to the negative 2x. Which would be negative 2x minus 5 halves plus c e to the 2x. I'm just bringing it up and negating the exponent to make it a little nicer. All right, so that's the general solution to a differential equation, barring any minor calculation errors. I think they gave us a condition, right? What do they say here? Yeah, y of 0 equals negative 2. So we have to figure out what c is. So y of 0 equals negative 2. So negative 2 equals negative 2 times 0 minus 5 over 2 plus c e to the 2 times 0. So negative 2 equals negative 5 halves plus c. So I'm adding 5 halves to both sides. So that's going to be 1 half. Negative 4 halves plus 5 halves. So general solution becomes particular. Y equals negative 2x minus 5 halves plus 1 half e to the 2x. Phew, Jackman. That's some crazy stuff right there.